Without further ado, let's get started. Welcome, everyone. This is the part 3 presentation on lithium in batteries, and we're covering recycling. And this was kind of the reason we did this series in the first place. The part 1 and the part 2 were basically needed to get all the information in front of people to then talk about the recycling aspect of it. If you've missed those, the first video is online. The second one we're late releasing because we had to edit it a lot and we were too busy doing this. But those will all be available, and the presentations will be available so people can walk through and see all 3 pieces. So most of you know Jeff and I, so we're not going to introduce ourselves too much, but we both have, pretty deep backgrounds in lithium ion batteries and a lot of experience, and we like using those to share some of what we know with the rest of you on topics that we think are interesting, and we hope that you do as well. And Erika, if you'd like to introduce yourself, and then Luke and your company real quick.
Hi, everyone. I've been in technology since 2013, and I was the program manager at Romeo Power, then did a joint venture with Warner, and from there I opened up Electric Goddess, which is a research and development firm. We do a lot of different things in batteries, but mostly focused on space batteries at this point, which is like my dream because I want to build space hotels one day. And then we had a lot of our clients ask us, how do I recycle batteries? They're spending a lot of money on moving logistics and they don't know what to do. And so that's kind of how we got into recycling, to just provide a solution for our clients. And it's been a fun adventure. And this is my partner, Luke.
Hey, my name is Luke. Been in batteries a long time, from data centers to zero motorcycles to Joby Aviation and Airbus, and learned a lot with Ferrisys. Worked all over the world, and love to do research and development. And I'm grateful for this opportunity in battery recycling to change the world. And I've made so much to scrap, putting nails and crushing and shorting so many different battery packs all over for your clients. So it's great to have a good way to return those into useful materials now.
Okay, so quick recap from our part 1 and 2, just sort of the high level stuff so we can jump straight into the recycling. Jeff, take it away.
Yeah, so just to make this quick and painless for everybody, basically part 1, we went over why everybody wants lithium, and it really boiled down to is it gives you a lot more capacity and energy, which is what everybody wants, is they desire to make things smaller and live longer. We also covered kind of the preamble to part 2, which was, how much lithium you need in actually a pack to make it work. Like the example here, 10 kilograms in a 60 kilowatt hour pack. It's what the Chevy Bolt uses, and this is not lithium carbonate equivalent. We do everything here is pure lithium. And then in part 2, what we really did is we said, okay, everybody wants lithium. Let's talk about the mining and all the logistics associated with it. So what we did is we not only covered all the mines and this timelines. We put together a timeline for building up a lithium mine. We covered the complexities associated with it, whether you're getting it from brine or from spodumene. And then we also kind of covered, people tend to have this misnomer around lithium efficiency, which is essentially dependent on which chemistry uses the lithium most efficiently. And what it really came down to is a cell design decision. Yes, LFP per amp hour will use it most efficiently, but that means you're having to make trade-offs elsewhere that you might not be comfortable with. And then from that, we just kind of concluded, some preferences and consumers need to shift, because if you look at the mining demand that needs to be in place and the demand for longer range, the real problem to this is just who is the consumer and what are their expectations of the product. And today we'll cover with that unreasonable consumer, what is their expectations from recycling as well.
Thank you, Jeff. And now, Erika, tell us why we need to recycle batteries.
A very small percentage of batteries is actually recycled, and Aubert and I will get into this later on, where we see what happens when cells and batteries accidentally get thrown away into trash cans or the wrong recycling center. What I always say about recycling is the recycling circularity starts with reduce. So it's very important that we reduce the amount of scrap first, but eventually everything will need to be recycled, and getting those critical energy materials back without the gnarly mining that goes on is very helpful for us. So that's one, is protecting the environment, reusing the materials we've already got out of the earth, and then reducing fires in trash trucks, transit stations, landfills. Another thing I like is that it creates jobs and economic abundance. So it's not just like, I think garbage people make a lot of money. Like, I think they're union workers and it's like a pretty good job. And so that could definitely be translated to recycling. And then what's really cool from a scientific perspective is we have so much room to advance in material science and recycling, especially with purity issues or contaminants. There's so much room to do amazing things with materials that will not only be for recycling batteries, but I can see it be applied to many different industries.
All right. Thank you, Erica. I'm going to move on to the next slide now,
So
which is Jeff.
yeah, so guys, we're going to be a little paced. There's a lot of information that needs to come in recycling. So the first one here is we're changing things up a little bit. So we've basically put together a data set and we have some modeling assumptions. As you know, Bloomberg, Benchmark Minerals, the S&P, McKinsey, they all give out different demand factors, different scalings. So what we've done is we've actually created a data set with the averages of all their predicted gigawatt hour demands. Additionally, we've created and gathered all the mineral reserves and production data for what are we producing today, what are we forecasting to produce, what have we historically produced, what was the annual production rate, and done a linear regression to kind of balance out what the market realism versus optimism is. And then we've also created kind of a material demand based not only on the gigawatt hours projected, but also some floating other aspects such as consumer market and other large scale markets, right? And if you look at it, right, some of the material demand, right, 70 million vehicles is what everyone's predicting. That kind of jives with the 67 million vehicles sold annually a year. And then you can look at the growth factors, 2.3%, and then you can use that to help drive your further cost. And there's a bunch more math involved in this. But that's kind of the assumptions you were going with. And then if you guys ever want access to this, just buy us a coffee and we'll happily send you the data set, because I drank a lot of coffee doing this and I want to return on that coffee investment when I started making all these data sets. So with Aubert. So next slide.
I think real quickly before we jump into that, there was a good question that I think it's important to cover now, which is can we compare expert analytics with the rigor of systematic reviews? And that is a great point and question. And one of the biggest problems Jeff and I have is, we even have access to paid reports, but the public data that's available for a lot of the predictions on any of the material supplies, any of the gigafactory production, any of the recycling capacity, any of the mining, refining, it's all over the place. And the ranges on the spreads as you go forward in time are like this. I mean, it's like people with very conservative estimates, people with extremely big ones. And so I 100% agree. There needs to be much better systematic review of a lot of these numbers. And so this is our shorthand attempt in, a month of our spare time to bring a lot of those together and kind of show some trends and points. So that's what Jeff just explained the assumptions are, and we'll go to those now.
Yeah, so if you look at the next slide here, I think a lot of you will remember this chart. This is essentially what everybody predicts the gigawatt hour demand curve is going to look like all the way out to 2055. And I intentionally capped it for various reasons that there has to be something. And I figure in 30 years we'll hit that. And then what we're going to do is look at two scenarios, right? One is kind of that question towards that question. One is the systematic review, right, done on our side, and then one is what we call the rocket ship or the market optimism that is being fueled by Benchmark Minerals and Benchmark Intelligence. So this is just what we've all seen. There's a great link down here to someone who's called Peter Zahein, who's a geopolitical strategist who also talks about EVs and then also talks about the realities of production and stuff. And I know the first question is going to be is if somebody looks back like lithium production for the last 10 years, it clearly doubled. But the reason it doubled is because the mines just essentially went to max capacity. They didn't actually create new mines or create new facilities. Australia came to save the day because they were operating at like 50% capacity. So like it's easy for you to increase supply if you're just never at capped capacity for a mine. So if you go to this next slide, this is what we call the market optimism versus realism. So what I did here is on the realism side, we assumed basically a 20.5% annual growth rate of lithium production for all the markets. So if you can already look at it, right, basically by 2040, we cap out. There's no world that you actually are able to meet the increasing demand beyond 2040. And if you were at our last talk, right, that means they would have to be building lithium mines today in order to meet this demand in the future. Because the timeline for a lithium mine is almost like 15 to 20 years, and that assumes perfect flow. You don't get any bureaucrats, you don't get any political hangups. Everything you predicted is good. And that's the deadline right there. And if you actually look at the last 10 years of data systematically, 20.5% is optimistic. If you look at essentially the data for the last 10 years of lithium production, it's roughly 13.5% annual growth rate if you look at the last 10 years. So even me giving it an additional 7% is being generous. So the main takeaway here, guys, really is like, yes, 2035, we probably meet the Bloomberg benchmark minerals intelligence demand curve, but once you exceed that timeline, you're not hitting it. And it's just a function of there's no way you can bring up more than 20% capacity annually without having to build new mines or make things more efficient. And even if you look at like direct lithium extraction out of the waste brine from mines, even if you bring that up a little bit, you're still shot between 2040 and 2045 because there's only so much efficiency you can get back out of your process, right? So going on, this also brings in another interesting one, right? Which is, when do we run out of other things? Because we talk about lithium a lot. So if you go to the next slide, Aubert. Here is the remaining production capacity of the different elements that go into our current battery packs as a function of time. And you can kind of see policy kind of trends with this, right? Cobalt and nickel kind of run in a standstill at 2030, which brings the oh shit LFP crowd to the forefront, where they start saying LFP becomes the biggest contributor. Also, you have to deal with the fact that 46% of the global worldwide reserves of cobalt come from the Congo. So whatever policy you have in place, you're basically having to police production inside the Congo. And then manganese, you're out about 2036, 2040 on remaining production capacity. Now, this assumes, I think each of these assumes basically a historical data taking the annual increase in production capacity for each of those specific minerals projected out in time. So not all of these are linear trades, right? So for example, nickel production, I think, is like 6.1% annually is what it's historically been capable of doing. Lithium is still the 20% and all of that. And even lithium starts running out a little bit early. Right, so it's 2030, even lithium will start becoming kind of an issue if we look at it. So even LFP won't be immune to this because lithium is actually going to be the one driving all the other minerals, which is going to bring what I hope to answer in the next couple slides with Erika, Luke, and Aubert, the recycling question: where should the focus be? Next one. Oh yeah. Last one. So this is sorry, Aubert and I did this and it was interesting. So we created 2 case studies. We basically said 90% of all EVs recycled, 45% for years 0 to 5, 45% years 6 to 10, and then 90% efficiency in recycling the lithium. And then in case 2, which is the more pessimistic, which is 50% of all EVs recycled. To Fran, to your question, and to Maynard, yes, if we get into different chemistries, that could help alleviate load, but then you're having to de-risk the consumer. And what I would say is, if you can convince the consumer, the answer is yes, and then can recycling help offset the load? That's kind of what this is showing. So you have cases 1 and 2, and you have the total kilograms of lithium demand, and you can see that the bigger issue here is the efficiency of recycling said EVs and then the associated timeline with recycling those EVs, right? If you buy a Tesla today, the reality is the person will own it for like 5 years. So you don't get that lithium back for 5 years. And then you have also the associated efficiencies with recycling that lithium. So if we say case 1 in the most optimistic case, you still can't even bring lithium in to meet market supply. And in case 2, it's significantly worse, right? So it's kind of points to the idea that, yes, we do need to recycle, but we need to do it, and we do need to do it soon. But even then, you would still need to short or supply recycled production lithium if it meant purity. You would still need to supplement that with mines. just because of how the cycle of cars works and how some people hold cars for 10 years, some people hold cars for 15, 5, right? And that becomes the bigger issue with trying to get these curves to the correct point.
And two quick things to add in, one is that currently a lot of planned and existing recycling capacity doesn't look like it's going to be recovering the lithium. And ultimately, we'll cover this more later, but it comes down to the cost question of, are they going to be able to make money recovering the lithium, which really just depends on the lithium prices. We've got some slides on that shortly. There's some great discussions going on in the chat right now. And basically, to Linda Gaines's point, yes, the recycling cannot cover the growth requirements. So what you kind of see is at 2040, assuming kind of the EVs a year sort of sit at the 90 to 95 million, sort of kind of hit steady state production, then 5 to 10 years out from that, you start getting a steady state production of lithium being plugged back in. And so it can cover the ongoing amounts of lithium, but it can't cover the growth requirements. That has to be the mines and refineries, but it can help offset it on kind of a 5 to 10 year period. And that's why we really wanted to show this slide. So thank you for asking the question that kind of points to our point of this slide.
Yeah, and one other thing to just caveat there, guys, right, is like you would have to hit steady state with a demand curve for you to ever have recycling meet demand, because recycling is a reactionary process, right? And then even then, assuming demand was constant, efficiencies is never 100%, right? So you'll never, ever be able to fully supplement your demand with recycling, just because you can never hit 100% efficiency with something. That's, I mean, anybody who does that, talk to me, we'll start a business, we'll make some money, and we'll go from there.
Okay, so we're going to jump ahead to the next one. So I believe this is now going to be Luke walking us through just a quick overview of sort of some of the different ways batteries are recycled in processes. And then we've got a more detailed flow chart of the same stuff afterwards.
So as Aubert says, this is for the visual audience. So what we've kind of broken down here is the direct pyro and hydrometallurgy, and Luke's going to be helping me out here. This is kind of a very, what I would say, like rough brush stroke, right? So hydrometallurgy, we have kind of essentially an activation, separation. We go through a leaching process. We precipitate out what we wanted to leach or what we want to recover. We then separate that, and then that becomes dried. And then essentially we push that out the door. Pyro, kind of as it sounds, you take packs, you shred them, you burn it into black mass, black mass actually comes from the shredding. You then burn it into a slag and you try to recover what you want as a metal, whether that be the cobalt, the nickel, or whatever has got the highest spot price. And then direct, it sounds like it is, and it's actually more effective for if a cell hasn't been filled with electrolyte, because electrolyte is the bane of all existences. But basically direct, you're just taking essentially the assembled cells and you're just recovering directly from the cathodes and stuff through separation. Luke, anything you want to add into this?
Yeah, just direct recycling works fantastic if it's new cell material, so cell maker, scrap, fallout. Pyrometallurgy normally today is done at existing nickel smelters where they just add in some feedstock of batteries and it's exported. The non-transition metals, non-high value transition metals like nickel, cobalt are exported out in their slag content debris with their normal mining slag. So it's a modified processing. Hydrometallurgy usually involves a step to break the binder to either a roasting or sonication stage. Yeah, that's a good rundown of the three basic paths people use.
We see a lot of combinations of these too.
Yep, there are many combinations, and almost everybody uses an electro stage somewhere as well. Even a pyromet guy will probably have an electro stage at some point as well.
And just for clarity, could you just say one or two advantages and disadvantages each for pyro versus hydro right now before we then get to the downstream?
Yeah, pyro, I guess, real quick, you can do a lot real quickly. It's faster process. Hydro is a slower process. The downsides of pyro is recovery isn't as efficient, and the upside of hydro is recovery is more efficient, and you can usually get higher purity materials out of it.
If you have a good slag for pyro, you can get very high metal purity from it as well. You know, we left out a process like 6K or a magnetron cavity with plasma, but a process like this is essentially a pyro modification that doesn't use combustion energy, but RF energy in that case as its thermal source to generate a similar process. But they could use plasma condensate temperature control to control crystal size. So it's a cool advantage in reforming material.
So if you go to the next slide, we have this in a kind of a more detailed flow diagram for everybody. So this is actually how the process flow goes in. You got some sort of waste lithium ion. It's going to come in really two flavors, individual discrete cells or in a kind of a module form, and they will both go through some form of dismantling. From that dismantling, they'll probably separate out everything from the module side, the plastics, the steel, the BMS. That then slag actually goes down into pyro, which where they're smelting, and as Luke pointed out, right, you're getting out an alloy. Whatever you can't take, you can take to construction and do it, and then the rest is flue dust, which gets used in various other things. From the alloy, you actually run it into the hydro process, and you can do leaching and other things. And this is to Luke's point about combinations of multiple things, because as they try to refine the processes. And then on the right, we actually have the whole hydro flow diagram. So you can kind of see how everything flows into each other, and they tend to take from each other and mix processes together, and get different things out of those processes. And I think, you know, Luke could probably comment on this. This isn't set in stone if they use a zigzag classifier, if they use air sieving. Some people will use different methods to separate stuff out differently based on what's most efficient for their process. And I think Luke and Erika will give you guys a great insights later on into how they do it at their shop. But really, the one thing I want to highlight here, guys, is this great quote from Andrew Abbott, which is the current method of simply shredding everything and trying to purify a complex mixture results in expensive processes with low value products, right? And that's not always true, right? It depends a lot on what you're trying to recover out of that. But if you were to like throw 15 types of different black masses into one recycling line, it may not yield you the best results, right? So the real here is with minimal hope of standardization between cell producers, it's going to just keep making this process really challenging.
Well, as a counterpoint to Andrew Abbott, I would say any process that relies on humans to disassemble the batteries is a totally unrealistic pipe dream that would never scale for human life safety reasons. So the challenge to solve is how do you separate it out after you shredded it, and that's at least 50% of the whole challenge in material recovery battery recycling. That's why it's a difficult challenge to solve.
Yeah.
I mean,
and we're going to be covering all of those challenges in the next couple slides. Anything else to say on this, guys, or can we move to the next one?
No, I think we're good.
Okay, so there are a lot of challenges in recycling, and we're going to be covering them sort of in order of kind of not necessarily difficulty, but where we see the pain. And so one of the first ones really is basically the problem of you're transporting the safety and passivation is how we title it, but basically you're transporting what will probably be live cells, at least at some state of charge, and you're going to have to basically handle, ship, store, aggregate, ship again, store, handle, and then process in some way. And there are ever-evolving enormous requirements for battery shipping regulations and now also storage regulations because of how unsafe they are. And I'm not going to go deeply into that. We've got other videos on safety, and you can kind of read some of this stuff here, and there's links. But the key thing is that passivation, which is basically removing the energy from the cells before you're shipping them and storing them and handling them, is very challenging and difficult, even for professionals like us that know what we're doing. Cells are all very different. The packs are all very different. And it's very difficult for especially the public to know just when they drop something off, outside of Best Buy for their laptop battery disposal, there's no way for them to know if it's discharged fully or other things. And then you've got a bunch of these different state of charge things sitting together, and one goes off and they all go off. And we'll cover that a little bit more. Anything else you want to add to that, Erika?
It's the important first step of battery recycling is getting it to the recycling facility. So it's a big problem.
Safely. So
Yeah.
the next problem, there's the safety piece, and then there's sort of the logistics piece. And so there's lots of regulations for shipping batteries and for transporting them, which are ever evolving because they're keeping battery fires from batteries that pass those regulations and requirements. And so we've all seen sort of the shipping container fires. We've seen the different, airplane fires, the truck fires. And those are huge, huge expensive safety concerns. And so it's getting more and more expensive and more difficult to ship batteries. And ultimately, used batteries have unknowns in them that make them inherently more dangerous to ship because you don't have the control you have as they're exiting a factory. And they're in conditions where maybe they're damaged or abused. And so all it takes is one cell going off. And we've got a great example in the next slide to talk about that. Anything else, Erika, you want to add?
No, you're doing great.
Okay, thank you. So this is a fun thing that, sorry, not a fun thing. This is a horrible thing, but it's a time appropriate thing that I just found that happened last month, where basically on the 14th of July, a MetroSite recycling center in Banks County, Georgia, basically they're next to an SK battery factory, and they're not supposed to be shipped batteries. This is not a battery recycling center. This is a material recycling center. They're just supposed to get scrap. And what ended up happening is they keep getting batteries shipped with their scrap that are live. And what happened is basically one of them went off, and you can see they did this autopsy after the entire facility burned down. And they basically found that it was started by a couple lithium ion batteries. And by the end of it, they found a whole bunch of live lithium ion batteries that were in the supposedly safe scrap that they were given. And it burned down their entire facility. There's a lawsuit asking for $26 million of damages. And this happened, like literally the fire department is next door to them. They responded immediately. They sprayed 3 million gallons of water on them before it extinguished 4 days later. Like that's almost a best case scenario in terms of like your next door neighbors, the fire department, they have all the, the things right there to try to help the problem. Still a complete loss. A couple batteries that were slipped into a normal waste stream. And this place is not even supposed to be handling them in mass anyway, right? So I thought this was just a really nice example of kind of the dangers of what can happen during this. Again, lack of passivation, multiple waste streams, and not being ready for it. And Erika, anything else?
I think that's a really great example. It's not only just recycling centers, but also trash centers. So we throw away batteries in the trash. And so this happens even if it's not recycled improperly. It just happens at landfills or transit stations.
We talked with a garbage truck maker too, who said that they lose a truck every day of the year to people throwing batteries in the trash cans. They have one garbage truck that burns down somewhere in the country every day from batteries thrown in the trash. So that won't scale with insurance and losses of buying vehicles for long.
And this is a problem that everyone has in the battery industry. So if you talk to any battery manufacturer, they probably have a shipping container in the back of their lot that no one likes to talk about, that they like shove all their skeletons in there because they don't know how to ship them, because how do you get the energy out of them, like we were talking about a few slides ago, and then how do you ship them, especially if it's going to cost you thousands of dollars to do it. Many companies don't have that type of budget at this time.
In my day job, because I build prototype cells and then test them in sometimes abusive ways, we have to dispose of a lot of basically hazardously created cycled prototype batteries that haven't even gone through the normal regulations and testing, UL and UN and stuff like that. And so the answer is you end up paying hundreds of dollars per like 1 amp hour cell to dispose of them, right?
Mm-hmm.
So orders of magnitude more than the value of the cell just for disposal. That's not recycling. That's not discharging for shipping and recycling. That is like hazardous waste disposal with all the bells and whistles to do it safely. So this is just a really big problem that being in the industry, a lot of us see that it doesn't really feel like it's the people that are doing the policy planning or some of the sort of recycling at scale facilities have a good solution for it yet. And we'll get to some possible ones for those later when we get to Erika and Luke's slides. So I'm going to go over this very, very quickly. There's a couple fantastic slides in the Volta Foundation Battery Report from last year, the 2022 one. This one goes over sort of the supply chain complexity, where you can see kind of the different interrelationships between where things go and how they happen, and sort of the policy and recycling. I'm not going to cover it much here, but if you're interested in that, you can go find that and a bunch of other interesting things on recycling and Second Life in the Volta Foundation Battery Report. So the next thing we're going to be covering is black mass, and we're going to give you a this intro on what it is, how it's hard to classify, and why this is a big problem. And I forget if it's, oh, this is my slide. Great, fantastic. Okay, so I'll be talking now. But basically, black mass is one of the outputs you get from battery recycling, and it's comprised of all of the valuable things that you're hoping to then refine out and extract once you've recycled the battery. So the cobalt, the nickel, the manganese, the copper, depending on the process, the lithium. But basically, you collect the batteries, you discharge them, you shred them. The metals are separated out from all the other junk. And then you end up with this shiny metallic mixture called black mass. And the problem is that depending on the feedstock, which we will cover more in the next slide, they can be very, very, very different in what is in black mass from this company versus this company, or honestly, even this batch of batteries at the same company versus the next batch of batteries at the same company. If they were made with LCO cells versus LFP cells, completely different materials you're going to get back out. And that's sort of the problem, is that then when you have this black mass, how do you value it? How do you sell it? Who can use it? How do you incorporate it back into the basically refining to materials to battery build process? And there's also the added issue that, you know, we talked about the batteries ending up in the trash stream. Well, there's also other trash that ends up in the battery stream, and you can get wrong types of classified batteries, the lead acid, the nickel zinc, the nickel metal hydride, other new technologies as they come out, and also just trash. And there's so many different chemistries that sometimes those can really interfere with the processes that you're trying to do to recover some of the materials if you don't know that those contaminants are there. Anything else real quickly, Luke or Jeff, before I jump to the next?
So we got one in the chat from Linda wanting to discuss the difference between handling EV batteries versus portables. And I think, Luke, you'd probably be a better thing in what are the major differences in handling those two types of different inputs to the recycling
That's
process?
a good question, but I think, can we handle that in the after discussion? Just because from a time perspective, we're already kind of running over for this. The short answer is scale. Little batteries cause smaller explosions and fires, and big batteries cause bigger ones, but we'll talk about the handling requirements for those when we talk afterwards. So here, next. And I'll try to go quickly on this, but basically the standardization of black mass basically depends on standardization of the inputs of the batteries, the processes used to refine them, and that's how you can kind of sort of standardize the black mass outputs. But there really isn't that yet. And so what's happened is the industry has almost done the opposite, where Benchmark just came out with basically a cool, here's like a bunch of different versions of black mass, and here's how we're going to price them all. And while that does help people then value it for how to buy and sell it, that's the opposite of standardization. That's sort of making it okay to not have a standardization for it. There's also different grades of black mass, and so premium versus basically okay versus bad, and those really depend again on the inputs coming in and the process. And I don't know if you want to say a few words on this, Luke, real quickly before we jump to the next one.
Just that everybody seems to have their own definition. You know, some makers like to have the lithium pulled from it. Some people like to have no plastic in it and binder already stripped. Some people want no foils in it, just metal oxide cathode active materials. So yeah, everybody's got a different definition of black mass. Kind of strange, actually, in an industry, I think. Okay.
So next up, the next one. So black mass and standardization is one of the big problems moving the recycling, industry forward. One of the next ones is, of course, cost, and it's cost versus basically sustainable and green practices and things that are better for the environment, but that nobody's paying for.
Yeah,
and that's one of the next big things we want to talk about.
I'll go into the basics of this. Basically, there was a comment earlier in the chat about unionization and human labor and increases in human labor, and the answer is yes. All of that directly impacts the recycling costs until you get it fully automated. Basically, what's happening here is a diagram of If you were to ship it around the US in a truck, if you're shipping it around in the US in a train, you're paying $1.73 for truck, $1.56 for train, just because the train can move more. And then if you were to ship it to China via a truck and then throw it on an ocean tanker to China, it's $2.20. But because labor is so cheap in China, actually it's more cost effective to recycle in China than it is in the States, right? And I don't think we're all unaware of that as a reality. So, some of the assumptions to this are quickly just 800 tons a year for hydro is what makes it profitable. 700 tons a year for direct is what.
And real quickly, Jeff, I think Luke was trying to say something, and I'm gonna guess, Luke, it was that's if you're doing it by hand, which is why in the US we're trying to do it in automated ways. Is that what you're gonna say?
Yeah, I was just going to say our process uses almost zero human labor for the entire process, which is the other side of it, where labor cost is, nothing, because I don't see it ever scaling or being practical to have humans disassembling them from a life safety perspective. They're damaged, defective, recalled packs, not good packs that you're disassembling. They randomly short and burn all the time.
Yeah, and the trade-off for that is, of course, basically, lower cost human labor on one side with safety issues versus on the other side, automated stuff that has higher CapEx costs, right? Probably. That's sort of probably the trade.
Yep, definitely higher CapEx.
Okay, so Jeff, continue.
Yeah. So basically, you guys, Luke and Aubert, kind of covered the whole thing here. In the U.S., right, we're probably going to move away from having cost of the human element go down, just because we're going to automate things a lot more. There's a lot of liabilities associated with this, so we'll have to reach and look at it there, really, from that point of view. But I think we should stop here if this is
so really the things we wanted to highlight are the different cost basis of how you're doing this, and basically that a lot of the cost models have all been developed really around the nickel and the cobalt. And so the profitability a lot of times has basically been pegged to the cobalt prices and the nickel prices. And so there's kind of the joke in the battery recycling industry that, everything would be solved in battery recycling. It would all work. It would all make sense if all you have to do is just put 1 pound of gold in every battery and everything will get recycled. And cobalt was basically that gold. It was so valuable that it was really worth recycling back when it was LCO. But the farther away you go from that towards LFP, that sort of monetary incentive to get the cobalt back goes away. And so again, like we mentioned earlier and Luke talked about, for LFP, it's the copper and it's the lithium. And if those two things don't pencil out to the same cost that it takes to, again, passivate, gather, handle, aggregate, bring, shred, process, and then refine to sell for a company, it's not going to happen. And that's really one of the things that we're worried about. And we'll talk about a couple of those things a little bit more in a minute. Anything else that you want to say, Luke or Erika? Actually, there's something I want you to specifically to say, Luke. So the very last point on this slide was, basically refineries have no easy way to hit really high purity with lithium. And Luke made my favorite comment in this entire presentation when we were doing the planning, which is battery grade lithium is very fussy. So could you say a word or two about that, Luke?
Yeah, so commercial lithium had been to supply the greases market. Lithium greases are pretty excellent, used throughout industry, and ceramics and glass glazing applications, at which case, they considered 3 nines to 4 nines purity lithium as a high purity material. And of course, battery grade had to, they have to make their own special agreements with that particular provider to even come up with a standard that's high enough purity, because the normal metrics for commodity products, don't go high enough for the levels that cell makers accept. So, and electrolyte makers accept.
Okay, thank you, Luke. We're gonna jump to the next slide. All right, Jeff.
Yeah, so this is kind of similar to the previous slide, and what it really does is it's looking at the NCX chemistries versus the LFP chemistries, right? And where does in the timeline it makes sense. And the unfortunate reality is the value for LFP doesn't really make sense with the current costs of recycling. Now there's a world where this changes. And that world is if lithium actually gets more and more expensive, right? Lithium prices keep going up, then there's reason to gather the lithium, which means getting the lithium back out of the LFP makes a lot more sense. But as it currently stands, with cobalt and nickel being the main cost drivers or the main, things on the London exchange market with the highest spot prices, that's what refiners are going to focus on. And it's kind of what Aubert said in the last slide, right? Unless the recycling produces the material at value and it makes sense to buy it cheaper from the recycler at price of the market, it's never going to be cost effective. And then companies are just not going to bother with it.
Yeah. And there's lots of caveats on that. There's subsidies, penalties, other incentives, equivalent carbon taxes put on stuff. But the main point is that it has to be economic to do it if we want it to actually take off and be prevalent. And right now, Luke and Erika, when we were talking to them, really highlighted that the difference in recycling with the current, basically when the lithium prices spiked, made such an enormous difference in the profitability of the recycling, because that's especially for LFP, that's basically the primary component you're getting back out. Mm-hmm. And even if it's not going directly back into, lithium batteries because of a purity issue, which is actually a big problem, is that you need much higher purity, which is much more refining, which is much more expensive. To refine the lithium for battery grade. Basically, regardless of that, if the lithium price is very high, that all makes sense. And if it's low, it doesn't, and it won't happen. Anything else you two want to add?
Nope, we're good for my end.
Okay. Okay, so real quickly on just legislation, and we've talked about this a little bit, but basically, the one on the left is just one example of, Redwood Materials effectively lobbying to change the responsibility, which basically means who pays for who's going to be doing the recycling. And there's people talking about making either the battery producers or the OEMs themselves be responsible for basically collection and recycling the products, and putting the onus on them with some kind of regulations or taxes or something like that, at penalties if they don't do it, or even incentives for doing it. So that's one approach. The other one is basically from a subsidy perspective for the critical materials in the clean vehicles tax credits, right? And so we're all familiar with those, so I won't spend too much time, but basically they're ramping up the percent of each material that's required to be basically made, processed in the US to qualify for those credits. And since a lot of those materials don't come from the US, one way to do that is to basically bring in a percentage of recycled materials into your battery production stream. And so if you do that, your vehicles get these very big, nice subsidies, and then the consumers are more likely to buy your vehicle. And so not being able to hit this really hurts companies. So there will be some incentive to buy recycled materials and maybe bleed them in at 3, 6, 9%, even if there's some problems with purity or cost. So anything else you guys want to say about that, Luke or Erika? Okay.
I think that there's a lot more legislation to be done, and basically recyclers have to lobby at this point, because many of the people in the EPA, Department of Transportation, don't know what to make for laws at this point, and it's very gray.
Yeah. And basically, the legislation here almost has to offset the safety legislation and requirements that are coming out that are driving the costs up, right? We had a question earlier about unionization. Well, costs go up. More safety requirements for shipping and handling, costs go up, right? So all of those things make it harder and more unlikely that things will be recycled. And so you need something on the other side to counterbalance it. So really quickly, I'm just flashing this again. There's great resources out there. This is one of the few slides we're showing that's not from the Volta battery report, but basically regulations also governing the minimum battery life we think are critical, because basically the longer the materials sit in the battery and get a longer life cycle, the more efficiently used they are from an environmental perspective. So we'll talk more about this later, but one of kind of our conclusions is that longer lasting batteries, which have to be basically required because there's so many conflicting asks right now, basically long drive range versus fast charging versus low cost. All three of those things actually really hurt the battery lifespan. And so, you know, when you drive down cost, you drive down quality. When you drive up fast charging, you drive down life performance. When you drive up the size of the battery pack, you make it less efficient, right? So all of those are things that basically have to be worked on very carefully, and that's consumer regulations, but also consumer preferences that are going to have to be talked about. Anything else from anyone else before I jump to the next one? Okay. So, and then again, you know, the regulatory framework, as Erika said, there's an enormous amount of stuff that's being talked about and coming through the pipeline. But there's a lot of work that needs to be done to make sure that those are correct and the incentives actually help, and that there's not too many of those cost adders not accompanied by things that reduce it. And so, you know, for everything that helps the recycling, there's something else that comes from a safety or environmental aspect that hurts it. And so we just need to make sure that the actual incentives are a net positive from a regulatory perspective. Okay. Last, just to mention, you know, second life is something people talk about a lot, and this has a really important place in between the first life use of a battery, especially for EVs, and the end step of recycling it to get it back to be made in again is, you know, can you use it in some sort of second life application that, you know, makes sense and is safe, that helps you extend the usefulness and the total life cycle per carbon footprint of the battery. And Luke and Erika did a great video on this, which you can find right here at this link. There's a couple other ones as well where people talk about sort of some of the economics and other problems with this as well. Do you want to say anything really quick, Luke and Erika?
We just touch on the engineering reasons on why we're generally opposed to Second Life at this point.
Just because they're not designed well enough to survive first life yet for most products, and that's the reason why. It's not like Second Life is a bad idea. It's just that you need a pack that is safe even through life one, as you know, step one to achieve.
So once recyclers only receive like mangled packs or packs that are completely dead, then you're at a good point to start Second Life.
Yeah, at this point, we receive basically 0 packs that someone just wore the cells out from use. That's essentially something we've not seen yet.
Also, another like interesting catch-all or Second Life, guys, that you have to understand is like most battery manufacturers test to whatever their application design's EOL is, right? And most applications that have high cycle life, they're looking at 70 or 80% end of life of original capacity as when they say, okay, that battery is done, right? So the reality is most manufacturers may test to 60, but nobody knows really what happens from like 60 to 0 as the cell continues to cycle.
And that's a huge problem too, because as Jeff and I can tell you from a lot of experience, and I'm sure Luke can as well, batteries have a tendency of doing this and then kneeing at some point. And so you can't just have the cycle life here out to 80 to 60% and predict that's what it's going to do all the way down. You actually have to have tested those batteries all the way out to see what they do all the way out. And that is extremely time consuming and expensive.
Their internal gas production seems to hockey stick up as that capacity knees down too.
Yeah, it's a situation, guys.
Corrosion or environmental conditions or anything else. So complicated topic, very interesting one, but we're going to jump back into recycling now. But very interesting, and we recommend all of you go read about this too, because it's very interesting. So real quickly, there's no great like gigafactory picture equivalent for recyclers. And so I was really hoping to just find and steal one slide that showed like all the recyclers in the world and just be able to highlight them. But the only one I could find was in Europe. So this highlights some of the different European recycling efforts, and then talks about the North America entrance over there on the left. And then what I've also done is I've added in a couple of the other companies that we're not talking about elsewhere. So we are skipping Redivivus and Redwood Materials on this list, but just highlighting kind of here's all the big players and here's where they are, and sort of here's what their kind of investment level is and kind of what their pitch is for what they're doing, what technology they're using to recycle. Again, in general, the battery recycling is not our topic, it's just the lithium piece. So I'm just going to kind of show this for a couple more seconds, and then we're going to jump to the next slide, unless anybody wants to say anything more on this right now. I'll take that as a no.
Awesome.
And jump to the next slide. So again, lot of people working on this, a lot of companies in the space. And so there's a lot of different technologies and combinations of technologies and processes people are running, different business plans, different input streams, different output streams that people are looking at for this. It's a very busy space right now. But again, we're focusing on the lithium piece of it. So I'm going to keep this up for 1 or 2 more seconds, and then we're going to jump forward again. Okay. And this slide and the next 2 ones, again, are in the Volta Foundation Battery Report. And so this lists some of the collaborations and joint ventures in recycling. This next one lists some of the investment level that's planned by who and who's working with who. Again, a lot of global interest in this. And again, a lot of this is unfortunately right now not going to be recovering the lithium, which is one of our kind of big concerns for this presentation. And of course, the adjustment from them, they kind of did this planning when things were still NMC or LCO, and now it's LFP, and that really changes what the story is going to be and kind of how that all pencils out economically. So again, those slides and more are available on the Volta Foundation Battery Report. And so we now come to our first case study on looking at sort of like one company in the recycling space. I'm sure all of you have heard of Redwood Materials. And we're going to just kind of go over them really quickly, just some of the financials and numbers for them, what they're doing, kind of what their value proposition in play is. And then after that, we're going to contrast it to Redivivus and what kind of their company and technology is, which I'm really excited about.
Yeah, and the way to look at this, guys, is we're looking at 2 different plays in the same market, and how those 2 different plays yield different outcomes, right?
And the last thing we'll look at really briefly is just kind of a quick example of basically building a recycling center for the scrap, a direct recycling center, kind of next to a gigafactory. And we'll briefly kind of review some of the pros and cons of that are, but since there's not a great example of that yet, we don't have a case study for it. So real quickly, so Redwood Materials, right, they've gotten a lot of money, and that $2.8 or $2.9 billion of money raised includes a $2 billion DOE loan. So this is a very highly funded company and activity, and they're basically all hands forward right now on what I would call an economy of scale and vertical integration play, where they're basically trying to get an enormous amount of the used batteries in the United States coming in, mining, refining and processing them. And then their other thing is they want to be a cathode maker. So they're not just going to be selling the materials to other people. They're going to use them themselves to make cathodes. And basically that's, the nickel or the cobalt and the lithium, make the cathodes themselves. And that way sort of vertically integrate from a cost play perspective, where they get as big as possible, they get as many batteries as possible, they sell as much cathode as possible, and that's their play to be successful economically. So they have a lot of kind of goals in what they're saying there. They have the made in US, recycled in US material source play. They're going to get IRA money, they're going to get DOE funding. There's going to be an increased incentive to buy their materials, again, as the critical materials requirements and the tax refunds scale up. So right now they've got about 500 people on LinkedIn. They're building a huge facility in Nevada, which actually I put a link on the next page where you can look at all of the tax incentives that Nevada and the federal government are giving them to do that, which are enormous, and what they promised to do for it. And so they promised to add 701 jobs in Nevada by 2029. And to basically bring in a lot of tax revenue and generate a lot of business there in Nevada and be shipping out cathode.
Yeah, and what I would take, guys, a lot of this, right, when we look at like a company like Redwood Materials and a lot of the claims is just take them as face value claims, right? There's similar to the battery industry, there are plenty of companies that claim 6,000 watt hours per kg or some ludicrous number because some marketing person added an extra 0. But remember, just take these things as claims, because like anything else, our recycling was kind of last to the party. And as they develop their recycling processes, cell manufacturers are developing new cells. So they're kind of dealing with a moving target where they need to figure out, hey, Panasonic decided to use like PVDF HFP now versus PVDF, and that's completely killed our, essentially our break apart process of getting the cathode off the foil. So remember that a lot of this is long lead time, and the claims are usually small scale, not gigatons or megatons of production in a lab somewhere in a beaker.
So just real quickly, and you know, Luke, jump in at any time, or Erica, but basically Redwood's play, get batteries and battery packs, take them apart. Currently by hand, they're working on scaling that up. They're looking at different processes. They're at least saying that they have a multi-pyrohydro process. What they use and how that works is going to depend on, again, the feedstock and the economics of it. But their basic premise is they're going to recover cobalt, graphite, which we'll see, lithium and copper, and then basically take those materials and plug them back into the battery industry specifically, is what they claim they're going to be doing, which means, again, higher purities and higher refining costs. And then they themselves want to basically refine the cathode materials to the point where they can be a cathode producer, which is going to be rewarding from an economy of scale and vertical integration perspective, where they can pocket a couple different companies worth of margin stacking if it works, but also add a lot of difficulty, because now not only do they have to deal with all of the recycling issues, they have to deal with all of the cathode production issues as a company that hasn't done that before in a country that doesn't really do that. So it's a big, again, it's a scale play. And we just have to wait and see if the amount of money they've gotten will let them kind of do that successfully or not. I think that's kind of the way that's going to turn out. And then, of
kind
course, the
of
economies of the outputs.
Kind of the Fran's comment here, right, is because they're developing, the cost of those materials to get them to battery grade is really unknown versus the fresh out of the mine and refined stuff, right? Like, they're making an MC, and we just don't know what level of grade that is, how it performs, and all of that stuff, right? And that's going to be tribal to them as they continue to work on their processes.
Yeah. And the last thing I want to say, and Luke and Erica, feel free to jump in at any time, but the last thing I want to say is really what I also view the biggest problem for Redwood is it's not just how much money they can get in to offset their basically scale and CapEx requirements, but I think because they have to get a huge amount of batteries to make this giant project work, they're going to be the ones that are really suffering from the early problems of the passivation, the logistics, the transportation, the shipping, the insurance, the storage, and the handling. And conveniently, there's a great company that sort of seems to solve a lot of those problems. And unless there's something you want to say before I jump to your slides, I'm going to jump to your slides.
I did want to say something about Redwood. I really appreciate what they're doing and the fact that they're going at it from a large scale. I think what gets a little confusing to the public eye is there's kind of two different things that they're working on, right? There's the feedstock they get directly from the Panasonic line, which is a lot easier to create new cathode material on. But what's really interesting is a cell maker is going to try as hard as they can to get less and less and less manufacturing fallout. So no matter how many they're making, that is an industry that's going to be continuously shrinking. And then there's the secondary part where you see a lot of pictures on this slide where they do have people taking apart these batteries so they can get to the cell material. And that's going to be more of a challenge and more costly to get to that cathode material, especially as Luke has had experience 10 years ago working in a cell maker where they were able to get 95% of the purity and 95% of the performance of the cathode material, but it costs more money. And I know it's been 10 years from there, but that's kind of like the journey that we're on there.
And high nickel cathodes don't tend to recalcinate to original performance, unlike LFP cathode material, which does tend to have a good recalcination process to recover good crystal structure to be a good cathode material.
Mm-hmm. Yeah, and on Luke's point there, that's why you see people talking about bleeding back in the recycled materials at some percentage with pristine, which helps that a little bit, right? So, but that's a logistics and how you piece that all together, piece of the puzzle. All right, ready for our next case study, and I will hand this off to Luke and Erika.
Thanks, Aubert. We started a battery recycling company originally to make metals for the metal industry. So we created nickel cobalt pigs, copper pigs. We gave them to the largest foundries in the US. They were like, this is awesome. It's 99.99% pure. It's great feedstock. It didn't cost us very much. Like, we've actually made money being able to provide this material. But the really big difference between we were ahead of our time with doing battery materials into aerospace and secondary markets, is that there's kind of this general rhetoric in the world with batteries where it has to go back into batteries, right? These elements can go anywhere, right? They can be infinitely recycled. But because we were very much ahead of that, we decided to kind of pivot. We really took a step back and we're like, what are the biggest problems in battery recycling? And there's really three. So there's the passivation that we've been talking about, how to get the energy out. There's logistics, how do you not have it cost so much and be so dangerous? And then three is material recovery. So if you like basically look up battery recycling on the internet, you're just going to get a bunch of like search hits on material recovery. And then when you're creating technology guidance, our ethos is we really want to respect human life. So I've personally seen someone take a high voltage across the chest. It's a pretty scary thing. You know, it smells kind of bad, but I'm glad that they lived. And then respecting the environment. So there's reusing of the water, reusing of solvents, little to no VOC releases. These are all things that you can start optimizing with different today processes. And then the third thing is we want to start small by creating processes that make money. A lot of processes are negative, and I know that worked 10 years ago to create businesses that maybe started as a negative profit, but that doesn't really make sense like long term, because in order for people to adopt recycling, they have to actually make money, because that's kind of how capitalism works. And because of that, we decided to address a major pain point in the industry, and that's providing the transportation. So if you go to the next slide, Aubert, this is a mock-up. We actually have a minimum viable product now where we're actually cryogenically shredding batteries, but we've designed a system that shows up on site to dealerships, recycling centers, anywhere there's batteries that are collecting, so like EV makers, and then you're able on site to be able to shred the batteries. And why that's important is because the Department of Transportation classifies them as non-hazmat material, hazardous material. So you don't need to do class 9 shipping, which is like seriously the highest cost, where I've seen it all the way from $3 a pound to $12 a pound to ship stuff.
Also, when she says shred the batteries, we mean cryogenically blast freeze to a safe temperature, shred the batteries, and then the shreds are dropped into a neutralization solution where the stored chemical potential energy is released thermally into that aqueous solution to dissipate that stored energy from charge, so that the end result is that the stored chemical potential energy has reached a low energy state. Just to clarify, so that people don't interject in the comments with you know, if you just freeze it and shred it, what happens when the shred's warm? And yeah, they'll burn when they warm afterwards if you don't neutralize it.
It's actually the biggest question we get is, why do you need to neutralize it? And that's because, you know, 30 minutes later they can catch on fire. But our shredder works with cells, modules, packs. Basically DER is what we're targeting, because recycling really needs to be batteries that can't be cycled anymore, and that's what we're preparing for. And if you're a battery manufacturer, your battery is not going to end up on eBay, which we've seen a bunch, so you get a certificate of destruction right on site. And that's kind of our view. It's a precursor to black mass. In the neutralization system, we're able to like tune it to whatever the end recycler needs. So Redwood materials.
I was going to say the big advantage to the system is all of the other options to recycle this impose the transportation logistics risk that once you've loaded a truck full of damaged, defective, recalled batteries, regardless of whether you use the appropriate packaging or not, it is a serious fire risk to the truck, you know, to a road hazard, you know, the whole thing. So with this system, you never actually have the truck roll while there's a damaged, defective, or recalled battery with energy stored in it. The truck only rolls after everything has achieved neutralization. The slurry is neutralized.
And so just to kind of jump in, like the thing that I think is so cool about this is it basically solves what I see as really the biggest challenge for scaling this, which is the logistics safety passivation issue. And really, there's no one else that's focusing on that. And this is a wonderful, basically, you could almost view it as a component in the recycling process where cool, then maybe every OEM has a couple of these trucks to go pick up from their dealerships, or every municipality has one to go pick up recycled batteries from local storage. And even companies like Redwood Materials, maybe they have a fleet, and what those cars do is they just run around picking up the batteries, making them. If you can do it, I mean, there's an expense to buy them and set up that fleet, but it solves really one of the biggest problems. And I think if you do it this way and do it correctly, you're going to get away from a lot of the safety incidences and the enormous insurance and liability and lawsuits that you'll get otherwise. Because if things exist, if things continue the way they do right now for the basically consumer electronics battery recycling, it's just dead. It will not work, because even those have a high enough incidence rate and problem. And when you add car batteries to the mix, the safety risk when one of those goes off is just astronomically bigger.
Yeah, and you guys got to also remember too, right? Like this not only solves the transportation logistic cost associated issue, this also solves some of the human element, right? When you start putting full packs into something, right, that is part of your labor or OpEx cost that is going into this process, right? Unfortunately, what is valued to recycle will always be dependent on what is the hot ticket of that year in terms of either that's lithium pricing or cobalt or nickel or what have you. But the real goal here is to reduce the other unassociated things that go with it, or the OpEx costs associated with it.
And again, in the US, where labor is more expensive, especially with the IRA funding things, basically that defrays the CapEx cost and lowers the average cost going forward. So from all of those perspectives, this kind of thing just fits in kind of perfectly. And it lets the recycling company then not worry about logistics and shipping and insurance and lawsuits, and just work on the recycling piece of it, which is already complicated enough, as hopefully we've illustrated today in the rest of the presentation.
Yeah, and one thing that we haven't covered, guys, that's good, is remember, recycling doesn't have to be recycled into batteries. There are plenty of other industries that use cobalt and stuff at a lower grade than what the battery industry standardizes against, and are just as profitable. So like, if you can't narrow the worldview to this has to make its way back into a battery. The lithium can go into grease. We all use grease every day. Grease is a great thing, so there's plenty of options out there to make this profitable, and it's just a matter of looking at what are those alternative solutions. And a lot of the market, or a lot of the industry, tends to focus solely on how do I get it back into a battery, and that's great and fantastic. But remember, you have to fund yourself to that point, and the only way to do that is to sell it to other things.
Okay, and so this is our second to last slide, guys. We're finally almost over. I see a couple people with their hands up. We'll take your questions momentarily, and if you want to just throw them in chat for now, we'll at least have them saved there to get to quickly, so you don't have to hold your peace for too long. So last thing we want to look at really briefly, and we'll keep this pretty quick because we've covered a lot of this sort of by talking, but basically this is sort of the last sort of case, which is sort of a direct recycler, or really what that means is a scrap recycler. So you're not handling live cells, you're handling basically the waste stream coming out of the battery gigafactories. This, it's relevant to where, if you're next to a Tesla factory, you're also getting all the bent and broken frames and everything else like that. But basically from our perspective, from a lithium perspective, what basically this is one, there's probably not as much in these, but you either have basically a cell maker themselves who's installing a direct recycling facility or line that's co-located with their battery line. And what that just lets them do is recover the scrap and lose less money as their yields scale from very low to higher as they ramp, especially new production lines. And so the con is that the more efficient the production, the less this facility is needed because there's less scrap, and then the less economic it makes to maintain it. So that is a negative. They sort of, people talk about it as cannibalizing their own demand as you get more efficient. But the pro is that it vertically integrates. And so, and also lets them keep control of those key materials so that they're not having to then increase their basically their material supply chain to keep up with, you know, hey, a 50% scrap rate as they're bringing their facility online. They're getting to kind of bring some of that back in and reincorporate it, reuse it, or even send it back to their refining partner to kind of keep the cycle going.
This kind of brings up a point Xiaojing just made, guys. Like, there is not going to be a silver bullet process that recycles everything equally or as effectively, right? Like it's kind of a misnomer, right? You have to design a process to meet your expected inputs, right? So if you don't know your expected inputs, you're always going to be trying to hit a moving target, right? And that's why, for example, scrap recycling out of a factory makes tons of sense, because one, the factory wants to reclaim. Two, they don't really care if the equipment gets used less because they want higher yields. And three, they know exactly what should be going into those materials, right? Like Panasonic knows exactly what their binder formulation is. So they can design a process exactly around their binder formulation to recapture everything and make it useful, right? So those are the things you have to think about, right? And this goes to my earlier comment, right? Yeah, it's great holistically to say, let's get these back into batteries, but the first step should be, let's get these back into something.
Okay, so, and now, sorry, we didn't cover the other one, but basically if a company does this as a service for somebody, the kind of cons are then you're not margin stacking, you're either co-located and getting ever diminishing yields by that factory, or you're shipping stuff farther away, which is a cost negative. And then the same kind of pros of somebody doing it themselves from a vertical integration perspective, where they're basically, when they want to control the materials and being able to vertically integrate, those are the cons from that business model. So there's a lot more to this, but we're going to jump to our conclusion slide since we're down to 2 minutes left. So we've spent an hour and 20 minutes on what was supposed to be a 40-minute presentation, which we apologize for. Hopefully you're still enjoying it because you're all still here. So here's our last slide. And this is sort of our conclusions, or maybe our worries might be another way to put it. But we try to always, and especially with Luke and Erika, who are so positive about everything, we try to have it be more of a sort of solution possibilities and challenges to overcome, not problems and issues. But basically the goal of all of this that we always need to keep track of is really the reason we're doing all of this in the first place is our desire to create a world where we have basically a net zero footprint. And that is the thing that we always need to keep our eye on the prize for through all of the EV production and recycling and everything else we're doing, is making sure that that is what we're serving at the end of the day, not just trying to commercialize a new product with a 5-year life cycle where you're replacing a new battery pack and throwing them away in the lithium every 5 years. There's a risk that could happen if we don't all stay on target. And there's a lot of ways to mitigate that and improve that, and some kind of positive things that can happen to make that better. But really everything needs to be viewed from that lens, in addition to the technology and chemistry, practical applications, and the cost drivers of the economics for it when you look at manufacturing.
Mm-hmm.
Agreed. Right, Jeff, you want to go through the design solutions?
Yeah, so the make cells that last longer is a pretty good one from Jeff Dan. There's really 2 ways to achieve this, guys. You can either make the chemistry live longer via the cell you've designed, or you can make bigger batteries that discharge less. And those are basically your 2 effective ways to do it. Smaller packs is another great way to get some of these things figured out. I think from a point of view, everybody needing 300 miles, 400 miles of range on their car, doesn't really make sense, because everybody's basically budgeting for the 1 road trip or 2 road trips they take a year, which doesn't really, come on, guys, you're going to plug it in when you get back anyways. And then another thing is just protecting the batteries, right? So like, even in this world where you make a cell live longer and go longer, right, you still have to deal with things like corrosion of the metals, right? So even at some point, you make batteries that go a couple hundreds of thousand cycles, right? The packs they have to be in have to be essentially resistant to the environment that they're in.
Okay. So Erika and Luke, do you guys want to do the free market capitalism, or do you guys want to do the new technologies?
I think Luke is going to want new technologies.
Okay, I'll leave that for Luke, and
I'd love new technology.
Yeah.
Okay, then I'll grab capitalism since I'm the finance adjacent person. Okay, so basically, you know, at least in the US, it is a free market capitalist system, despite the subsidies and regulations and everything else in there. And really cost is king. And so legislation that mandates cell recycling or incentives to encourage the behavior are very, very important, and they need to overcome all the hurdles here and everywhere else that the things like the unionization or the safety or the other problems end up bringing from a cost and challenge perspective, right? Also, building cells that are more likely to be recycled, standardizing the inputs, standardizing the chemistries, even to some degree the size and the ways they're built. The same type of cylindricals, for example, are easier to handle than a whole bunch of different pouch cell or prismatic types in some ways. And then lastly, you know, efficiently using the lithium, which Jeff and I talked about in our last presentation. And, you know, if we're making cells that use, you know, if we're making pure lithium metal cells, which use a lot more lithium per energy density, if lithium is one of the scarce components and it's one of the environmentally sort of complicated components, then maybe we should not be prioritizing those chemistries, especially for something as mass as EVs. I'm not saying lithium metal is going into EVs, it's just an example. But basically looking at things from a different perspective of not just a, you know, dollars per kilowatt hour, but a how much lithium per dollar per kilowatt hour you're using. And I think that as lithium scales up in price, which it's going to going forward, I have no doubt, is something that I think the market will help take care of itself. And now, Luke, the final words on the presentation are yours.
Right. So future recycling tech, you know, I mentioned 6K a minute ago. They have a microwave cavity resonator maser system to do plasma-based recycling, sorting, and cathode reformation. Of course, someone from 6K could say much better what they do if anybody on here is from 6K. So systems like this, or using lasers do the same thing, or even optical sorting mechanisms, including laser tweezers, are possibilities. You know, in a world where electricity is plentiful, and you want to recycle, those methods have the potential to be extremely high efficiency and high purity of output products. In a world where electricity isn't plentiful, and you have a lot of material to recycle, bio-leaching processes, you know, there's a genetically modified E. coli bacteria that complexes, organically complexes cobalt. There's one that organically complexes copper that's being used in commercial mining today, in bio-leaching mining of copper. And there's one for nickel. And so it would be possible, if you wanted to have a very low footprint and you had a lot of time on your hands and were willing to give it square footage, that the same way you handle waste management of a city with sewage and whatnot, you know, is with bio-leaching and treatment ponds. So you'd have to make your battery waste at the ideal pH temperature, ORP conditions for that particular bacteria to thrive in each one of the segments, and then you'd leach, you know, the copper, the cobalt, the nickel from your material. Probably, I don't know if there would ever be a lithium leach bacteria or not.
And then there's alternative lithium batteries.
Oh, sure. Also for the grid, of course, there's no reason to use lithium on the grid from the perspective that lithium is when you need it to be light and compact and small. And for grid storage batteries, of course, you know, it seems like a shame to use lithium in that application when you can use a slower, heavier ion, and it's not a penalty because the device is bolted to concrete anyways in a grid storage application. So I think that's one of the easiest, fastest ways to relieve lithium. That's no penalty to the user operating. You know, whether your grid storage batteries, lithium, sodium, magnesium, zinc, makes no difference to the user. You know, you just care that the grid was stabilized, so you don't have to carry it around with you in your pocket or anything.
Yeah,
But-
and there's really cool companies like, Form Energy doing their rust iron batteries and stuff like that, which are like, they're not lithium ion technologies, and they prioritize basically, safety is one aspect, but really it's just dollars per kilowatt hour cycle. And so lithium ion is too expensive to use in those industries. And so we're seeing other kind of cool technologies like that come out.
There's iron chloride cells that get below $10 per kilowatt hour of raw reagent materials, and there's some zinc iron batteries as well that get in the $15 per kilowatt hour range. Pretty amazingly cheap, if you don't care about size and weight.
Yeah, which for residential storage it's different, but for grid storage, ostensibly, you kind of have not unlimited, but less constraints for size and weight, which let that pencil out better.
Mhm.
You want to say a couple words about any maybe technologies you're excited about from like a refining or recycling perspective also? Like, is there anything you've seen people working on that you think would be really cool if it worked?
Other than our cryogenic shredder neutralization system.
Well, yes, but I don't know what I can talk about publicly. Sorry.
Okay, that's
Yeah.
fair. Jeff and I have that problem. So
Anyways.
I put you on the spot. So unless anyone else from our group has something else to say on this final slide, I think we're closing the presentation. Anything, Jeff, Erica, Luke?
No, I'm good from my end.
Great.
Okay.
Okay, we are now open to taking questions. You may all turn your mics back on. Try not to speak over each other too much, and looking forward to the questions and discussion.